Quantum mechanical calculations are clearly going to be easier and more accurate if our basis functions are as close as possible to the final eigenstates that they're going to represent. If you can imagine, if we actually knew the eigenstates in advance and could plug them into a Schrodinger equation, we would get our answer right away. We wouldn't have to do any calculation at all. Now I want to illustrate another sort of consideration that comes into play when making basis sets for these large electronic structure quantum calculations, and that has to do with the polarization of the wave function. I want you to imagine two hydrogen atoms, and I'm going to draw them out here in a very abstract form. Okay, hydrogen's in a 1s orbital, so I'll just draw that as a circle, but you can think of this as being really a sphere. So these are both 1s functions, and these two atoms are moving toward one another, and they're going to form a bond. All right, so now imagine what's happening as these two atoms get close to one another. We have a proton that's got a plus charge in the middle, and then we've got a cloud of electrons that are minus charge on the outside. And as these things get closer, the electrons are very light, and they can feel the positive charge of the nucleus on the other atom. They can also feel the negative charge of the electrons on the other atom. So what's going to happen as these two things get closer? Well, we know eventually what they will do is they will form a bonding orbital, a sigma orbital, that might look something like this. And I'm not trying to be very artistic here, but you get the idea that it's basically an elongated ellipsoidal type shape. All right, but what I will say is this, that if I were to simply take these two spheres, these are the atomic orbitals that we started with, and if I were to simply represent my molecular orbital over here, this is a sigma bonding orbital, I'll call it the 1 sigma g orbital. If I was to simply write that as the sum of these two s orbitals, those two s orbitals are spheres that are located on each of these atoms. Well, the two purple circles don't look a lot like that blue ellipsoid, do they? In fact, they're not very much alike, and so just based on the simple geometric analysis that two spheres do not equal an ellipsoid, we can tell that these two basis functions are not necessarily going to provide us with a great representation of this sigma molecular orbital. And in fact, it will be somewhat off. And we know from earlier calculations that, in fact, we don't get a very good or very accurate result for this. In fact, it's got an energy of about minus 1.099 atomic energy units, which, remember, are Hartrees. And it should be something more like 1.17. So it's not terrible. 1.17 versus 1.10, it's about 7% off, but that 7% off is largely due to the fact that these atomic orbitals are not very good at representing what this final molecular orbital is going to look like. So how can we fix that? Well, one way we might fix that is if we were to, for example, for each of these two hydrogen atomic orbitals, if we were to add a little bit of p character, in other words, add a little bit of this pz orbital to that s orbital, and do that for each of these, what would that do? Well, it would have the effect of allowing these two s orbitals to deform somewhat. So in other words, instead of being a sphere, now that s orbital might turn into something that looks more like this. And the other one might turn into something that looks more like this. So now when I add them together, I may get something that looks a lot more like the molecular orbital up here, so that I'm going to have a much better representation of my final wave function. And when I have a better representation of my final wave function, then I'll have essentially a better quality or better accuracy in my electronic energy levels. All right, so how would we set this up? Well, the way we designate this generally, and I'm going to use the 631G, which we talked about under the split valence basis sets. Okay, this is a valence basis set that says for the core orbitals I'm going to use 6 Gaussians. For the valence orbitals I'm going to use 3 Gaussians to represent the tighter part of the valence orbital, and 1 Gaussian to represent the more diffuse part of that orbital. All right, so that's how I would define what I'm doing here. But now I'm going to refine that a little bit by simply adding a star. Now, what does the star mean? In this case, the star means that I'm going to add some 3D character, 3D Slater type orbital character to my 2p orbitals. In other words, so this is a way of adding polarization. You know, this representation of these orbitals is a polarization of the spherical orbitals that we would ordinarily start with. When I add a little bit of 3D character to these 2p orbitals, this is a way of polarizing the p orbitals. All right, I can go further, though, to something that I'll call 631G star star. And when I do that, I have not only added this 3D character to the p orbitals, but this is in addition, I've added some 2p character to the 1s and 2s orbitals. In particular, the 2s, if they're the valence shell. So this way I've polarized the s orbitals. So these stars basically say the degree to which I have added polarization to these basis functions. And when they are more polarized, I should expect that I would get a little bit better result. Well, let me give you some results just so you can see how these compare. So I'm going to do this for several different basis sets. We're calculating the energy levels for H2, all right, which is the simplest molecule. And I'm sorry that I can't give you results for something more important. But if on this chart I have as my first basis set just the hydrogen atom orbitals. Okay, so I'm using things like 1s, 2s, etc. All right, those will be my energy levels. For the second basis set, I'm going to use a Slater type orbital, where the Slater type orbital is just represented by 3 simple Gaussians. For the third type, I'll use a split valence, which I'll call 321G. So the core orbitals are represented by 3 Gaussians, and the valence orbitals are represented by 2 Gaussians for the tight orbitals and 1 Gaussian for the loose orbital. Then we'll look at 631G, which is the one that we've highlighted up here and talked about a little bit. And then I'll show you the results for 631G star star. And finally, we'll give the exact results. Exact. All right, so these are the various basis sets that we'll use, and these are all going to be Hartree-Fock types of calculations, so I should specify that. All we're doing is using self-consistent field to optimize the parameters, to optimize the coefficients in front of the sum of the atomic orbitals that make up the molecular orbital. All right, so what sort of energy levels do we get from this? Well, I've already told you the result here. It's minus 1.099. These are all in atomic units. When I go to STO3G, I go to minus 1.117. So as we become more negative, remember this is an upper bound to that energy, so we're going to keep going negative. When we can't go negative anymore, that's basically the best we can do. So 321G goes down to 1.123. When I go to 631G, it's minus 1.127. Well, it looks like we're not going down as fast anymore. It turns out that we get a little bit of benefit from going to more Gaussians here, but not a lot. Okay, we've basically used up all our goodwill with that with a split valence basis set. But when we add polarization, we get even better. All right. It's about the same difference as doing this, but look, just by adding polarization, we got as much of a benefit from making this change as we did from adding all these more Gaussians going on this change. However, what is the exact result? It's minus 1.174. All right, so we are still quite a ways from getting here, and basically this is telling us that the correlation energy, remember the correlation energy is the difference between our Hartree-Fock result and the exact result, is still 0.043 atomic units. All right, so we're still quite a ways away, but I will say that this point here, we have really reached the limit for how well we can do. In other words, any further refinements to the basis set are not going to improve this energy at all. This is something called the Hartree-Fock limit. It is basically the best we can do based on the approximation that we're using a product of one electron wave functions to represent our molecular orbitals. Okay, the only way we can do better is by mixing those orbitals together, or by finding a different way of expressing the orbitals so that we're not using single electron orbital functions in a product format to get them. So under the assumptions of the Hartree-Fock approach, this is the best we can do, and we'll spend a little bit of time, very little bit of time, talking about how we go beyond that.